In continuation of the last videos on aromatic electrophilic substitution of BSc Part 1 Organic Chemistry, the topic we are going to take up in this video is directive influence of substituents. When a mono-substituted benzene derivative is treated with another substituting agent, then the substituent already present will affect the position and the rate of the reaction. Hence, we can say that the substituent already present affects both reactivity and orientation. There are many rules regarding the directive influence, and the first rule we take up is Crum-Brown and Gibson rule. Crum-Brown and Gibson rule states that if a group already present on the ring is X and its hydride HX can be directly oxidized to HOX, then the group X will be meta-directing, and if the hydride HX cannot be directly oxidized, then the group X will be ortho and para-directing. Now we take up some example. For example, if we take up halogens like chloro, bromo and ado, then we see their hydrides are HCl, HBr and HI, but it is seen that HCl, HBr and HI, they cannot be directly oxidized to HOCl, HOBr and HOI. Hence, chloro, bromo and ado are ortho and para-directing. Next we consider OH. The hydride of OH is HOH and it also cannot be directly oxidized to H2O2. Hence, it is also ortho para-directing. Next we come to NH2. Its hydride is NH3 and NH3 also cannot be directly oxidized to NH2OH. Hence, this is also ortho and para-directing. Now we consider CH3. Hydride of CH3 is CH4 and CH4 also cannot be directly oxidized to CH3OH. Hence, CH3 group is also ortho and para-directing. Now we come to nitro group. The hydride of nitro group is HNO2, which can be easily and directly oxidized to HNO3. So NO2 group is NO2 group is meta-directive. Now CHO group. The hydride of CHO group is HCHO and HCHO also can be directly oxidized to HCOOH. Hence, CHO group is also meta-directing. If we consider COH group, its hydride is HCOH, which can be directly oxidized to H2CO3. So COH group is also meta-directing. Now if we consider SO3H group, then its hydride is HSO3H, which can be easily and directly converted to H2SO4, that is, it can be directly oxidized to H2SO4. So SO3H is also meta-directing. Now we consider the limitations. It is seen that the hydride of OH is H2O, but in ordinary conditions H2O is not oxidized, although in the presence of UV light H2O may be directly oxidized to H2O2. So OH should be meta-directing at least in those cases. Now if we consider the hydride of CH3, it is CH4 and which may be directly oxidized to CH3OH under certain specific conditions. So CH3 group should also be meta-directing under those conditions, but it is always ortho and para-directing. Thus we see this rule does not fit all the substituents unless under all the varied conditions of reactions. So we see that this rule, that is the Crum-Brown's rule, does not fit all the substituents under all the varied conditions of reactions. The next rule is Wall-Landis rules. Those groups which show unsaturation such as COOH, NO2, CN, CHO, etc. are meta-directing, and whereas those groups which do not have unsaturation such as OH, Cl, Br, I, NH2, OR, CH3, they are ortho and para-directing. But if we consider the limitations of this rule, then we see that there are certain groups which are meta-directing although they are saturated. For example, CCl3 NH3 plus and NCH3 plus, they are saturated but they are meta-directing. While there are certain groups which are unsaturated and they are ortho and para-directing, like CHCH2 and NO, they are unsaturated but they are ortho and para-directing. Now we come to the next rule, that is Hammick and Illingworth rule. In a mono-substituted benzene derivative C6H5XY, where X is directly attached to the carbon atom of the benzene nucleus. Now if Y belongs to the higher group of the periodic table than the X, and if Y and X belongs to the same group and the atomic weight of Y is less than that of X, in that condition, that is in these two conditions, the XY group will be meta-directing. Secondly, if Y belongs to the lower group of the periodic table than X, or if only X is present, then under these two conditions, the group XY or X will be ortho and para-directing. Now we take some examples. In the first example we take is OH. O is X belonging to group 16. H is Y belonging to group 1. So it is ortho and para directing. That is OH is ortho and para directing. NH2 group, if we consider, then the nitrogen is X belonging to 15 number of group, that is 15th group, and hydrogen is Y belonging to the first group, so it is also ortho para directing, that is NH2 is ortho para directing. If we consider CH3, then carbon belongs to 14th group and hydrogen belongs to the first group, so CH3 is also ortho and para directing. Now if we come to NO2, here nitrogen is X and oxygen is Y, and nitrogen belongs to the 15th group and oxygen belongs to the 16th group, so NO2 is matter directing. And if we consider CN, carbon belongs to the 14th group and nitrogen belongs to the 15th group, so CN group is also matter directing. And if we consider CCl3, then carbon belongs to the 14th group and Cl, which is Y here, belongs to the 17th group, so CCl3 is also matter directing. This also has certain limitations, because if we see the composition of hydrogen, it is quite ambiguous in the periodic table, as it is considered to be the member of the group first as well as the member of the group 17th in the periodic table. So if hydrogen is taken as the member of the group first, then OH, CH3 and NH2, they are ortho and para directing. But if we consider hydrogen as the member of the group 17, then OH, CH3 and NH2 group will be matter directing. Now we come to the complex group, that is CHO. In CHO, if the carbon is X and if O is considered to be Y, then CHO is matter directive, as carbon belongs to the 14th group and oxygen belongs to the 16th group. But if we take carbon as X and hydrogen is considered as Y, then CHO will be ortho and para directing, because carbon is the 14th group member and hydrogen is the first group member. So these are various rules. Now we come to the effect of substituents, reactivity and orientation. On the basis of reactivity and effect, these substituents or substituted groups are divided into two types. Activating group. Activating groups are those groups which make the ring more active than benzene itself and are known as activating group. Deactivating groups are those groups which causes the ring to be less reactive than the benzene itself, and they are known as deactivating group. On the basis of the directive influence of the substituents, they are again divided into two groups, ortho and para directive. They are those groups which direct the incoming group to ortho and para position with respect to the group with respect to the group already present on the benzene ring. So the incoming group enters the positions which are ortho and para to the substituent which is already present. Second is meta directive, the groups which direct the incoming group to meta position with respect to the group which is already present on the benzene ring. Now we take the specific. Now first we take activating group and ortho and para directing group. Toluene is more reactive than benzene towards electrophilic substitution reaction. When benzene and toluene react with same electrophile, then it is found that toluene reacts at much lower temperature and lower concentration. That is, the electrophilic substitution reaction of toluene is faster than benzene. But if we take the example of nitration of toluene with concentrated HNO3 and concentrated H2SO4, then toluene forms nitrotoluene, and it is seen that it forms orthonitrotoluene 59%, para-nitrotoluene 37%, and meta-nitrotoluene 0.4%. So we see that the 96% of the mononitrotoluene is obtained as ortho and para product, while only 4% is obtained as meta product. So not only on nitration, but also in all electrophilic substitution reaction, we see that toluene forms ortho and para products in major quantity and meta in very negligible quantity, or it is also zero. So we see that we can conclude that CH3 group is activating as well as ortho and para directing. But we see that if there is a bulky group present, then it offers steric hindrance. If we see the example, this is tert-butyl benzene. This tert-butyl benzene on nitration forms 80% para product, 12% ortho product, and the major product is obtained as para product, and the major quantity is 80% of the para form, that is tert-butyl benzene, is due to the bulky size of the tert-butyl group which produces steric hindrance. So here we see at this carbon there is tert-butyl group, This hinders the incoming nitro group from approaching the position number 2 and 6, that is the ortho position to this third butyl group. And as the NO2 group is hindered and cannot approach the number 2 and 6 positions, the two ortho positions, it approaches the para positions much more easily. Hence 80% of the product is para product and only 12% is of the ortho product due to this direct hindrance of the third butyl group.